It's my great pleasure to welcome all of you to today's online seminar on interval methods in control engineering. And it's my great pleasure to welcome today Meng Zhou from the College of Electrical and Control Engineering of the North China University of Technology. And let me introduce our speaker. She received her Bachelor of Science degree from the Harbin Engineering University in 2011. Afterwards, she did her master's and PhD at the same university in 2013 and 2018, respectively. Afterwards, she's been a postdoc with the College of Information Science and Technology in Beijing, and she's currently professor at the School of Electrical and Control Engineering, and especially interested in multi-agent cooperation control, fault detection, and fault-tolerant control strategies. Yeah, and this is mostly already also a summary maybe of today's presentation title, where she will focus on event-triggered strategies for interval estimation and fault-tolerant control for multi-agent systems. Meng, the floor is yours.
Thank you. Okay. Thanks for professors. I'm very glad to take this opportunity to show my work of this paper. My name is Zhou Meng. I come from North China University of Technology. Today my topic is called event-triggered state in interval estimation and fault-tolerant control for multi-agent systems and the deception attacks. My talk mainly contains the following parts. First, let's talk about the backgrounds. We deal with the multi-agent systems. We all know that multi-agent systems consist of multi-autonomous agents that collaboration through distributed mechanisms, and they can achieve some complex tasks and solve problems. Nowadays, with the recent development of many technologies such as the IoT device and the cloud and the mobile network, we all know that the multi-agent systems may vulnerable to different kinds of attacks, mainly the network attacks. There are two kinds of common used network attacks that are denial of service, which is also called DOS attack, and another one is deception attack. In this work, we take the deception attacks at this one, and then it mainly deal with the fake date injection attacks. At this background, fault diagnosis and fault tolerance control for multi-agent systems are rapidly developed based on strict safety systems. We all know that the network attacks may occur through the channel from sensors to controllers, or from the controller to the actuator. In this work, we consider this from the sensor to controller. At this one, the network attacks, such as the deception attacks, is similar to sensor faults. To deal with this, we may face two questions. First one is how can a deception attack in a communication network be detected or estimated if we want to do the fault-tolerant control? The second one is how to design fault-tolerant controllers to achieve multi-agent formation. To deal with two questions, we do this work. For the first one, to how to deal with attack signal estimation. We all know that there exists a lot of fault estimation results. not only for the linear system, a non-linear system, or even for the multi-agent system, such as the robust observers, common filters, artificial intelligence-based methods, or other kind of parameter identification methods. But we want to know that most of them are only considered point estimation issues. Also, there are many results deal with the interval estimations, but for the multi-agent systems, we found that there is some open issues. To deal with the point estimations, it depends on accurate mathematical model. But in practice, it's very difficult to obtain this accurate model. Which makes the point estimation issue is very tough and difficult to achieve. So interval state estimation attracts many attentions due to it can deal with uncertainties present in the systems and make it easier to monitor. There are many kinds of interval estimations, interval estimation methods. Mainly, the methods can be divided into the following two parts: interval observers or set membership estimation approach. We deal with the interval estimation use the second one because we compared these two kinds of methods. We found that the membership estimation approach have the following advantages, such as it can deal with simple two steps. First of all, we can deal with an observer to achieve the point estimation, and then we can deal with the set membership estimation for the estimation error system, and we can obtain the interval state estimation. So it's very simple to operation. The second one, it can deal with the non-Gaussian and the non-linear uncertainty capacities. So based on these methods, we deal with the result of this paper. On the second one, how to deal with the fault-tolerant control for multi-agent systems to make the systems to guarantee a stable formation. We deal with a fault-tolerant consistence controller for these multi-agent systems if it deal with some network attacks. This is some of the backgrounds of the fault-tolerant consensus controller. We found that most results of the fault-tolerant control for multi-agent systems, they need to most of them ask the control input of the leader is 0. If the control input of the leader is not 0, most achieve the results may be difficult to maintain the multi-agents formation. But we know that the leader of the input should be time varying because it can change the formation based on the requirement. So we deal with this situation that the the control input of the leader is non-zero. On the second one is that we found most of the controller do not consider the robust design conditions. So based on the above aspects, the main work of our paper contains the following aspects. First, a set of distributed observers are designed for the uncertain multi-agent systems. The distributed observer is used to estimate the states and the deception attack signal. And when we design the distributed observers, we considered a dynamic event-triggered mechanism because it can preserve network results while maintaining the estimation accuracy. The third one, we considered the estimation results by the set membership methods. The upper and the lower bound of the state and also the deception attack signals can be generated. At last, fault-tolerant control is designed to achieve the formation, the multi-agent formation, and the leader-follower framework. Next, let's talk about the problem statement. In our work, we considered a multi-agent system which consists of one leader and n followers, and the system can be described like this. We assumed that the leader and the follower share the same dynamic systems. I means I is 0 means the system is the leader. From 1 to n means the followers. The objective of formation is that we need to design a consistent controller to make the followers can track the leader by a required formation. We need to deal with this and to design the controller with this structure. So the controller may need to estimate the state and also the input of the leader. This one is related to the input of the leader. So we need to estimate it. To achieve this result, we first we need to give some assumptions and lemmas. First one is the assumption we assumed that the disturbance T is unknown but bounded, and it can be described by a zonotope, which make us to generate the interval estimation of the states and the deception attacks by zonotopes. The main objective of this paper is to estimate the state and the deception attack signals, and then use estimated state to design a fault-tolerant controller to achieve a closed loop control performance. These are our leader and followers, and we can see that from the output channel, there is some deception attacks. So the output from other agents are wrong, and we need to, based on the information shared by the neighborhoods, to estimate the right state, and we need to design this a set of distributed observers to estimate the states, and then use the estimation result. So we can generate the by zonotope we can generate the interval result, and use the state estimation we can design the fault-tolerant controller. We will use the zonotope to generate the interval, so we can give them the definition of the zonotope and the properties. I think most of you are very familiar with this knowledge. Based on the linear operation and the minimal scale some property, we can make the process of the interval generation very easy. And this lemma can help us to keep the dimensional of the zonotope to guarantee a required dimension. This one can help us to this lemma will be used when we design the observers. Also, this lemma is also be used to when we generate the design conditions of the controller and the observers by using RMI technology. This one is used can be used to generate the controller matrix K. If we can generate a discrete time algebraic Descartes equation, we can use this lemma to generate the controller matrix K. The above are the problem statements. Next, we will talk about how to design the distributed observer for text and states estimation. The leader and the follower multi-agent system can be described like this. And now the problem is that we can how to estimate the states X and the deception attacks F. To deal with the F estimation is easier. First, we can treat this one as an another state like this, and then with this augmented technology, we can rewrite the system as this one. This one is a global multi-agent system. With this definition, from this definition, we can see that X bar means all the states. The states contains the deception attack signals, and under the undirected graph theory, we can rewrite the multi-agent system to a global multi-agent system at this. And now the problem for us is to estimate the augmented states X bar. And for this, it is easier. We can design a no input observer with the structure at this. This is the system, and at this, in this structure of the unknown input observer, the matrix J, K, and H are unknown, and that we need to design these three matrices. We designed each observer for each system. When we design the observer at this, we need to make this assumption that the matrix J and H should satisfy this. And now we don't know this term. This term in our papers is the neighborhood output estimation error, and it consists with the output estimation error between the the output of agent I and agent J, and also because we are considered the leader follower structure, we need to consider the estimation error from the agent I and the J, and between the S agent to the leader. So we need to add this term. Now this term we need to when we design this structure, the structure of the observers at this, we need to translate the output every time at K. when we want to reduce some network results, we can use the event-triggered mechanism. That means we don't translate the output every time. When it satisfies these conditions, the output can transform to the observer. Otherwise not. These conditions are the designed dynamic event triggered mechanism. It means that if this condition satisfied, the output k is update. Consists the following aspects. Delta means that the difference between the system output of yik at time k and the output that that triggered last time to meet the event triggered conditions and this. And this term is this one. It also neighborhood. It is also arrow between the each agents. And this term represents a dynamic threshold that can adapt it to the change of the output with this structure. And now we can see that there are some parameters in these conditions. If the following condition, the parameters are satisfied with this and these conditions, we can contend that this term is positive. And now if it satisfied this event triggered mechanism, the output can be updated. And so we can change this term, the yk, yik and yjk from this term to this one. Consider the arrow of between the output, and this can reduce some results. And now based on the structure like this, we can rewrite the observer. We can rewrite the observer structure as this. And now we need to design this observer with this assumption and some lemmas. We can rewrite it as this. And if it writes this, we can find a solution of the matrix J and H and this. J is a matrix that we can give it in advance. So based on this, we have know the matrix J and H. Now the problem is it changed that we need to solve the matrix K. Based on this, we can reconstruct an event triggered multi-system as this because it satisfies these conditions. And when we rewrite it as this, we can define a state estimation error between the global state and the observer. This is the observer state. This is the global multi-agent system. So we can this arrow the dynamic of this arrow. Also, we need to define the agent between the S follower and the leader. We need to analyze the arrow between them. We define the arrow as this, and we can rewrite a global arrow system between the follower and the leader as this. Next, we consider this one and this one together. we can generate an augmented feed system and this. Now the problem has changed to we need to design the observer matrix K based on this estimation error. And lemma theorem 1 gives gives design conditions of how to design the matrix K. If this LMI can be solved, then we can obtain the gain matrix K as this. And this conditions is derived based on the H infinity or L infinity and the Lyapunov stable theorem. After we obtained the point state estimation result based on the assumption of the disturbance is unknown but bounded, and also we make the arrow of this output at time k, and the time at the last one triggered the output. We need to assume that this term is also bounded and this. With these assumptions, we can derive the interval. We can derive the interval description of the arrow system. Because the point estimation we can generate by the above distributed observer, and if we got this interval of the arrow systems, we can obtain the interval state estimation. And the deception attacks has been considered in this vector. So after we got the interval estimation of this term, we can get the state and the detection attack signal together. And now, based on these equations, we can see that we can use the properties of zonotope. It can be easily to write it at this, and it is easier for us to obtain the theorem 2 when we update the center and the generation matrix of zonotope of the estimation error system. We can obtain the intervals. Now we have obtained the interval estimation of the states and the attacks. The next objection is that we need to design a fault-tolerant control based on the estimation result. At the beginning, I have shown you the structure of the consistent controller. It contains like this. We need the estimation result. Just now we have obtained this term, and now to deal with this, we need to solve this one and this one. This one is the matrix of the controller, and this one is related to the input of the leader. So next, our work has changed to how to design this and this. First one, we need to obtain the estimation of this term. To generate the estimation, we need to design another observer. Now, the objective for the multi-agent system to achieve a consensus, we need to make this objective. Now let's look at the state error of the S follower and the leader. We define it as this. And this we can after we put the description of this one and this one, we can obtain this. And this one is related to the input of the leader. We defined this one as this term. This is for this term. So we need to estimate this. If we estimate this, uh, we can use we put the controller into this. This is U, and this one can be minus this term. So we can achieve the state error of the follower and the leader to be 0. Now, how to design observer to estimate the system? We need to rewrite the system as this. We consider the term of the estimation error between the follower and the leader, and also this term. This term is related to the input input of the leader. And for this one, we need to design observer and this, and this FU is the matrix that we need to be designed. Based on a similar process, we can obtain the estimation error of leader tracking error at this, and then the dynamic of the leader of the tracking error system can be derived at this. Also, we can obtain its global description at this. Now, for this estimation error systems, our objective is to design the matrix FU to make this system maintain the area infinity robust performance. And this theorem 3 gives us the design conditions of how to calculate the matrix FU. If we can solve this LMI, then we can obtain this matrix. Okay, we can obtain this one. After we obtain the FU, we generally can generate the estimation of this term. Next, the next and the last problem is that how to design this term. This is a state feedback matrix. So we can the first one we can use the lemma to use the Likati iterations. Use the lemma flow. If we can solve the matrix P by this, and we can generate the matrix PU at this. This matrix can make the system make the open loop closed loop system is stable. So based on this, we can obtain this and this. The fault-tolerant consistent control has been achieved. But this one, if we obtain the matrix at this, we don't consider the event trigger. Actually, when we design the controller, we also can take the event triggered mechanism. So next, we designed another work to design a fault-tolerant controller with an event triggered mechanism. In these controllers, we consider a static event triggered mechanism as this, and these are the two terms. Under these mechanisms, we can rewrite the input. We can rewrite the control as this. We need to change this term and this term. Also, as similar, we can obtain the leader-follower error system at this. And also for this global error system, we can consider the H infinity robust performance and to design the matrix K. Theorem 4 gives us the design conditions to calculate the matrix Ku. That means if we can solve this LMI, we can obtain this matrix. And this kind of methods because we considered the H infinity robust performance, and also we considered the event triggered mechanism. Next is our simulation result. We take five aircrafts. Each aircraft the system described like this, and we in this paper we assume the followers and the leaders are the same, and we take the discrete time at this. We give the formation at this structure. These four followers need to track the trajectory of the leader. In the simulations, we set the parameters as this. These are the parameters that used to solve the observers and the controllers. Given these parameters, we can obtain the matrix of the controller and observers as this by using LMI toolbox. Also, we give some initial conditions and the disturbance and the control input. Also, we considered attack signal as this one. It is similar to a sensor fault. We assume that this kind of attack signal occurred in the agent one, and this result is a state interval estimation of agent one. We can see that we assumed that there are some attacks in agent one, but using our methods, we can obtain the right state estimation. Also, we can generate the state intervals. This is the attack estimation result. We can also generate the attack signals interval at this. The bottom one is that the triggered time. We can see that the proposed methods can dynamically adjusted the triggered times based on the output of the systems. We also make some comparison results. We compared the proposed method with some published results. It showed that this result is that we conduct 100 times, and then to obtain the average one. We can see that the proposed method can save the network communication results with fewer triggers times. This result shows the proposed fault-tolerant control effect. This is a state of each agent because there are four followers, and we can see that each followers can track the trajectories of the leader. This is a 3D diagram to show the effect of formation. This one is that we use a controller. We don't consider the fault-tolerant control. So we can see that after this time, when it occurs some attacks, the formation can't be guaranteed. While in our proposed methods, it can maintain the formations. To illustrate the effectiveness of the second fault-tolerant controller methods, we do another experiment result. We assume that the attack and this, and also we take it in agent one, and this are the metrics of the controllers. Also, we can see that under the proposed controller, the formation of the multi-agent systems can be guaranteed with the proposed fault-tolerant control. That if we don't consider the fault-tolerant control, it can't maintain the formation. And in this simulation, we changed the output of the input. We changed the output of the leader, and we can see that if we change the trajectory, the proposed method can also maintain it. This is that to show the effectiveness of the H infinity robust control performance. We compared it with these LQR controllers. We take the root mean square error to show the accuracy of the proposed methods. We can see that the error is smaller than the LQR controller. This is also show the trigger instant based on the proposed fault-tolerant control, because in the second one we also considered the event triggered mechanism, and this event triggered mechanism we also can maintain the state formation. At last, I will give the conclusions. In this work, a framework is proposed to address the challenge in multi-agent system and deception attacks. First, an interval estimation method is designed for the multi-agent system with a set of distributed observers and a zonotope technique. Second, a dynamic event trigger mechanism is proposed to avoid the communication and to relieve the pressures of the network results. Next, we design a consistent control of a tolerant control and event trigger mechanism to achieve the formation control. These are our future work. In this paper, an interval generation method is designed to estimate the deception attacks, but we don't use generate interval conditions when we design the fault-tolerant control. Actually, the generated interval informations contains the bounds of the states and the deception attacks. So we need to take these bounds when we design the fault-tolerant control. As a result, how to design the fault-tolerant consistent controller with the interval bounds is our future work. The next one, in this paper, the deception attacks is considered with a similar structure of the sensor fault. The structure of this kind of text is simple. In some existing results, we can find that the deception text is assumed to follow a Bernoulli distribution or other kind of probability distribution. So how to extend the proposed method in our work to this kind of attacks our another future work. Thanks for your attention.
And thank you a lot for your
talk.
presentation. And I'm pretty sure there will be some questions. Let's have a look at the audience.
Okay.
Yeah, I've written down 4 questions in the meantime. Maybe let me start. What you have presented during your presentation is, both in the estimation and also in the control design, a procedure that makes use of the assumption that you have homogeneous agents. Each of the agents is described with the same dynamics matrix, if I'm right. Is it possible to generalize your idea also to some heterogeneous agents, which may have different state dimensions locally for each of the agents, and which may also be described with different dynamics matrices and maybe also different control structures?
Yes. I'm sorry. I understand. I can't understand totally of your questions. I think you asked me uh, the proposed methods, how to use these two different systems, right?
How to
The large
generalize your method if you have, for example, let's say you have your 4 agents, the 4
Yes.
followers that you have described. And in your presentation, you have assumed that each of those 4 followers have the same dynamic system models.
Yes.
Is
If
it
there are
possible to
different,
generalize this to a case where all of those followers are described with different state equations with different dynamics?
no, we considered this we considered this problem when we designed the methods. If the systems of the followers are different, the global system we can't obtain the structure of the global system, and there's some result to deal with the 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 controller for different systems. But it may more difficult than this. So I think if they can deal with the problem to different multi-agent systems, maybe it may some challenge.
Yep. Okay, yeah. The second question that I have, your interval estimation scheme provides you with the bounds of the estimates and also of the deception attack. Your control strategy, on the other hand, this is relying, let's say, on a classical LQR design. Would it be reasonable also to handle, let's say, tracking errors resulting from the control strategies also in a set-valued framework? Because you're currently bounding the estimates quite tightly. You're getting guaranteed bounds even. But for the control design, you're using a non-guaranteed procedure. And somehow, at least from the outside, this looks a little bit imbalanced.
By imbalance.
Yeah, imbalanced from the fact that you get guaranteed bounds for the estimates.
Yes.
But for the tracking behavior, you're just using the classical tuning rules for an LQR, for a Riccati design, for example, without guaranteeing bounds on tracking errors.
Yes. When we design the controller, we don't consider the interval and we just use point estimation result.
Is then your assumption that, for example, if you have this formation, that, let's say, yeah, the deviation or the distances, let them be considered geometrically. You have, let's say, if I'm looking here at this figure, you may have an error of plus minus 5 meters, let's say, coming from the interval observer. Then you would assume that you're designing the desired trajectories, for example, for your individual followers in such a way that they're at least, let's say, 10 meters away of each other, that they definitely do not collide. Would this then be the kind of strategy, or how to exploit, let's say, those interval bounds for a safe design also of the control?
Yes, we don't consider this. We don't consider the distribute
Okay, but maybe
I
there's a
think
nice follow-up question to handle in the future.
yes, I think so.
Okay, do we have any other question from the audience? This does not seem to be the case. Last chance to ask a question, to unmute yourself and ask something. Yeah, if we do not have any further question, many thanks to you for this highly interesting presentation. As usual, we also put the slides on our seminar webpage. And yeah, I'm looking forward to meeting all of you again on Friday in 2 weeks for the next seminar. And until then, I either already wish you a nice evening, nice afternoon, and see you soon in the next seminar.
Thank you.